A functional concrete structure operates as a calibrated composite machine, constantly fighting invisible tensile and compressive forces. When internal balance fails, the collapse is instantaneous. The Indian Standard Code 456 enforces a rigid set of physical boundaries engineered to prevent these specific, catastrophic failure modes. For a site supervisor, the ultimate high-stakes challenge is verifying these complex mathematical steel arrangements in the real world, right before the wet concrete pour hides them forever. This graphic shows exactly what we are verifying: a complex structural node where a column, beam, and slab intersect. To understand how the code dictates this geometry, we must deconstruct this intersection layer by layer, working from the outside in. We will audit three distinct systems: the external environmental shielding, the transverse shear geometry, and the core longitudinal limits. Translating these code numbers into a spatial, visual checklist is the only method to guarantee both constructability and structural survival on site. We start at the outermost layer. Nominal cover is the exact physical thickness of concrete required to shield the internal steel from fire and oxidation. This diagram illustrates the core site recall acronym for environmental exposure, MMSVE. That stands for mild, moderate, severe, very severe, and extreme. The code dictates exact spatial requirements for each condition. Mild exposure requires 20 millimeters of concrete protection. Moderate exposure bumps that limit to 30 millimeters. As the hazard scales to severe, the required cover expands to 45 millimeters, and very severe pushes it to 50 millimeters. Finally, an extreme environment, like a tidal zone, demands a massive 75 millimeters of cover. Notice the mathematical jump sizes between these steps: +10, +15, +5, and +25. This sequence creates a rigid memorization anchor. The code permits two strict situational exceptions. The first applies to slabs. Under mild exposure, if the design uses bars 12 millimeters in diameter or smaller, the required cover drops slightly to 15 millimeters. The second exception applies to small columns. If a column has a minimum dimension of 200 millimeters or less and uses bars 12 millimeters or smaller, the cover drops to 25 millimeters. Nominal cover functions as a meticulously calibrated mathematical shield dictated directly by the local climate. Stripping away the outer concrete exposes the next structural layer, the transverse steel grids, made up of beam stirrups and column ties. This graphic demonstrates why beams rely on tightly spaced vertical loops of steel. Under high loads, a 45-degree diagonal shear crack will propagate directly upward from the bottom edge. If the vertical stirrups are spaced too widely, that 45-degree crack will cleanly sneak between them without crossing a single steel bar, resulting in immediate structural failure. By adjusting the stirrup spacing to exactly 0.75 times the effective depth, or D, we create an unavoidable geometric constraint. A 45-degree crack is now physically forced to intersect at least one steel bar. Therefore, the maximum permitted spacing for a beam stirrup is strictly the minimum of either 0.75 D or 300 millimeters. Columns require a different spacing geometry to prevent the main vertical bars from buckling outward. The spacing limit for column lateral ties relies on the rule LLD 16 phi 300. To apply this limit, the inspector calculates the least lateral dimension of the column, calculates 16 times the diameter of the smallest longitudinal bar, and considers the absolute maximum cap of 300 millimeters. The tightest or smallest of those three resulting numbers is the legal limit. While spacing grids handle shear and buckling, the physical diameter of the bars themselves introduces another constraint, particularly within the thin geometry of concrete slabs. The IS 456 slab thickness rule strictly limits the maximum diameter of any reinforcing bar to 1/8 of the total slab thickness, expressed as D/8. Placing a massive steel bar inside a thin slab acts precisely like this metal wedge. Without sufficient bulk concrete surrounding the rebar to maintain friction, the expanding steel simply splits the slab in half. These spacing and diameter limits function as physical nets, meticulously engineered to geometrically intercept specific structural failure modes. We finally reach the absolute center of the structural node. the thick, longitudinal main bars carrying the primary tension and compression loads. Core steel must operate in a strict Goldilocks zone. Minimum limits act as an insurance policy against sudden, brittle fracture when the concrete inevitably cracks, while maximum limits prevent dangerous voids during the concrete pour. For beams, the minimum tension steel is tracked by the mnemonic 0.85 is the fix-Y ratio. This represents the bare minimum volume of steel required to hold the beam together the split second the concrete cracks. The maximum limit for beams is remembered by the phrase, "beams are 4x4 vehicles." This represents a hard cap of 4% of the gross area for tension steel and 4% for compression steel. Columns follow their own parameters, summarized as columns are elegantly 0.8 built for to last 6. This graphic shows a top-down view of a rectangular column packed with the maximum 6% steel limit. That 6% limit is only legally permitted when bars are continuous. The moment those bars are lapped or spliced together, the allowable limit aggressively drops down to 4%. Overlapping bars instantly doubles the steel volume at that specific joint. This densely packed steel chokes the column, preventing wet concrete gravel from flowing through the cage, which creates dangerous structural voids known as honeycombing. To prevent the core from buckling, the code also enforces absolute minimums. Column bars can be no thinner than 12 millimeters, with at least 4 bars required to form the corners of a rectangular column and 6 to maintain the ring of a circular column. Slab minimums scale differently, dictated by the phrase, "slabs are thin, keep them sweet," 15 for mild, 12 for high heat. This dictates a minimum of 0.15% of the gross area for mild steel, but drops to 0.12% for high-yield strength deformed bars. Because HYSD bars possess higher tensile strength, the structure requires less physical volume to control temperature-induced cracking. These longitudinal limits dictate a precise engineering tightrope. They balance the absolute necessity of ductile tension strength against the physical reality of pouring wet concrete through a dense iron grid. Looking at this animated node, we can now see the entire structural intersection reassembled and ready to be verified as a single cohesive unit. Step 1 of the supervisor protocol is verifying the outer cover to guarantee environmental durability and fire resistance over the lifespan of the building. Step 2 is verifying the transverse steel spacing limits to mathematically guarantee the capture of shear forces and prevent geometric splitting. Step 3 is verifying the core longitudinal percentages to keep the structure inside the Goldilocks zone, ensuring it is strong enough to yield safely under stress, but open enough to pour smoothly. The provisions of IS 456 operate as the exact geometric translation of material physics. Master these physical limits, apply this spatial checklist on site, and you control the absolute structural integrity of the build.